Usually, when we think about a mechanical failure, there's this expectation of precision, right? Like if a piston cracks inside your car engine, you just plug a diagnostic tool into the dashboard. It throws a very specific alphanumeric code, and the mechanic just points to a screen and says, well, there's the problem.
Right, yeah. It's clean, it's binary.
Exactly. It's comforting, honestly. It's either broken or not broken.
But that's really just the illusion of total control, you know?
Yeah.
We desperately want mechanical systems to be visible and easily categorized. We want that clean diagnostic X-ray.
We do. But then you step into the actual reality of heavy industrial manufacturing. I mean, you walk into these massive, brutal environments, a steel plant, an open-pit copper mine, or some massive aggregate crushing facility.
Oh yeah, places that are handling literally thousands of tons of raw earth every single hour.
Right. And suddenly that clean diagnostic X-ray machine is just entirely useless. You aren't dealing with a static system that just cleanly snaps one day. You are operating in this landscape of continuous, chaotic, dynamic degradation.
It really is the absolute definition of diagnostic muddy waters. The scale of the destruction is so massive, but also so gradual that it almost becomes invisible to the people actually running the facility.
And that is exactly the hidden bottleneck we are pulling apart today. We're doing a deep dive into a mechanical failure in heavy industry that, well, that sounds incredibly niche, maybe even a little mundane at first.
Yeah, it doesn't sound very glamorous.
No, not at all. But it is currently bleeding global industries of millions of dollars in wasted material and putting human lives at profound physical risk every single day. The industry calls it conveyor belt mistracking.
Which, I have to say, has to be one of the most understated, polite terms for what is, in reality, a completely violent physical event happening on the factory floor.
It really is. I mean, a wandering rubber belt makes it sound like the conveyor at your local grocery store checkout is just squeaking a little bit.
Right, like it just needs a little oil.
Yeah, but when you are in a coal mine, a wandering belt creates a massive cascading failure. We're talking about tons of spilled raw materials, torn multi-million-dollar machinery, and really severe physical danger for the workers.
Absolutely.
But, what I find most compelling here isn't just the destruction, it's the counterinsurgency against it. We have this stack of sources today that paints just a wild picture of how this is being solved.
That's a great stack.
We are looking at granular product specifications and global case studies from Martin Engineering, and they are just absolute titans in bulk material handling.
They are. And we are contrasting that heavy hardware data with a completely different perspective, too. We have these highly technical repair diagnostics from Synchronix.
Right, the electronics firm.
Yeah, they're an industrial electronics firm based in India, and they deal with the harsh realities of what happens when you put delicate microchips into these brutal, dusty environments.
It's oil and water. And tying those two physical realities together, we have this fascinating operational manifesto from a system architect known simply as the Quiet Architect.
That document is brilliant.
It really is. It's essentially a playbook for how bootstrap startups are using incredibly clever asymmetrical billing strategies to step into these massive plants. They just bypass the traditional corporate purchasing systems entirely and turn spilled coal and iron ore into massive profits.
It is a perfect cross-section. You have the global hardware giant, the localized electronics repair specialists fighting humidity and vibration, and then the strategic framework of someone actively building a disruptive business model right in the middle of it all.
So it allows us to see not just what the physical problem is, but the deeply ingrained economic incentives that actually cause it to persist.
Exactly.
So, okay, let's establish the physical baseline first. What actually is a heavy industrial conveyor belt? Because if I picture a conveyor belt, I just picture a flat, black rubber road rolling over some metal tubes.
Right, that's the visual we all have. But the physical reality is so much more complex. To understand why these systems fail so catastrophically, you have to understand the foundational mechanics of how they operate. A heavy industrial conveyor belt operates entirely on a really delicate balance of two physical principles, tension and friction.
Okay, walk me through that. How does that actually look?
So you are dealing with a massive loop of vulcanized rubber. We should probably clarify what vulcanized means here because this isn't the rubber on the bottom of your shoe.
Right, it's not a sneaker.
No. Vulcanization is a heavy chemical process where sulfur is added to natural rubber and it's cured under immense heat and pressure. This creates chemical crosslinks between the polymer chains.
Oh, wow. So it changes the fundamental structure.
Exactly. It transforms the rubber from something that would literally melt in the summer sun or freeze and crack in the winter into this incredibly durable, rigid material that can withstand the impact of boulders being dropped onto it.
And they often reinforce it internally, right? Because I saw in the Martin engineering specs, they talk about steel cord reinforcement.
Yes, they do. For the highest tension applications, there are literally thick steel cables running longitudinally inside the rubber itself.
That is wild.
So you take this massive, heavy, steel-reinforced loop of vulcanized rubber, and you stretch it really tightly between a head pulley, which is the massive motorized drum at the discharge end that actually pulls the belt forward, and a tail pulley at the loading end.
And the tail pulley just spins freely.
Right. It spins freely and maintains the tension.
And then the whole belt is supported along the way by hundreds of smaller metal rollers, which I think the industry calls idlers.
Correct. The entire system relies on perfect, symmetrical tension across the entire width of the belt to keep it running straight down the center line of the rigid steel structural frame.
So if the tension is perfectly equal on both sides, the belt just runs perfectly straight.
Exactly. But the real world, especially the world of heavy industry, is never perfectly symmetrical.
No, of course not.
And that brings us to the core engineering conflict here, the dynamic load environment. See, the steel frame is static, it doesn't move. But the material being loaded onto the belt is entirely chaotic. Imagine a massive bucket loader dumping 3 tons of jagged limestone, or wet, sticky coal, or incredibly dense iron ore onto this moving belt.
It's definitely not gently placing it down. I mean, it's falling from a height, bouncing, settling completely unevenly.
Exactly. It never lands perfectly in the dead center. And when that material is loaded unevenly, even by just a few inches to the left or the right, the center of gravity of the entire moving mass shifts.
Right.
So the downward force on those idler rollers becomes unequal. The side of the belt with more weight grips the metal rollers differently, and that creates differential friction.
So the tension across the width of the belt is basically completely thrown off balance.
Yes. And because the system absolutely relies on equal tension to stay straight, that unequal tension physically forces the belt to begin drifting laterally.
It just wanders off.
Yeah, it physically wanders off its center line and starts moving sideways while it's moving forward. That is what the industry calls the drift.
And I really want to emphasize the violence of this for you listening, because this isn't a gentle wander. We are talking about thousands of tons of rock moving at high speeds. When that massive, heavy rubber belt drifts off center, what does it actually hit?
Well, it inevitably grinds against the rigid steel structural frame that holds the whole system up.
Ouch.
Yeah. The friction is just catastrophic. You have vulcanized rubber being dragged against heavy-gauge structural steel at hundreds of feet per minute under immense lateral pressure.
I was looking at a specific case study in the Martin engineering files, and the physical reality of this is staggering. They detail a situation at Minera del Norte's Semesa iron ore mining unit.
Right, the crushing conveyor.
Yes, their primary crushing conveyor was suffering from severe chronic mistracking. The drift was so pronounced, and the belt was in such constant grinding contact with the steel frame that the friction literally shaved the edges of the belt off.
It's hard to even picture that much force.
Over a relatively short period of time, the usable width of this highly expensive, heavy-duty industrial belt was reduced from 36 inches down to 32 inches.
4 inches of reinforced industrial rubber, completely vaporized into dust and smoke by sheer friction?
Which raises an obvious question for me, honestly. If this is a known problem, why wouldn't the original equipment manufacturers just design the steel frame with a giant metal lip or a heavy-duty guardrail along the sides so the belt physically can't drift off the edge?
It's a very logical question. I mean, anyone would ask that. But it fundamentally misunderstands the forces at play.
How so?
Well, if you put a rigid steel guardrail against the edge of the belt, you aren't actually stopping the drift. You are just concentrating the friction.
Oh, I see.
The unequal tension from that dynamic load is still pushing the belt sideways with thousands of pounds of force. So if it hits a guardrail, the edge of the belt will just curl up, fold over itself, and shred even faster. Or, in a lot of cases, the lateral force will literally snap the guardrail right off the frame. You just cannot physically contain a mistracking belt with a static wall.
So when you lose 4 inches of belt width to friction, a massive secondary problem occurs. Because the raw material, the iron ore or the coal that was supposed to sit on those 4 inches of rubber, has to go somewhere.
Right, and gravity pretty much dictates it goes straight down.
This creates what the industry calls fugitive material.
which is such a funny term.
It really is. It sounds like an escaped convict or something.
In terms of financial liability, it practically is an escaped convict. Fugitive material is just tons and tons of expensive, valuable raw material spilling endlessly off the sides of the belt and piling up beneath the conveyor structure.
It is literally their product, their actual profit just falling on the dirt floor.
Exactly.
And the psychology surrounding this spillage is fascinating to me. The Quiet Architect source points out a deeply ingrained, almost institutionalized flaw in plant management. Heavy industry often treats this spillage as an inevitable cost of doing business.
Yeah, they really do.
They look at a mountain of spilled coal under a conveyor and think, well, conveyors spill. That's just a fact of nature. Send a crew out there with shovels to sweep it up.
It's a massive, fundamental failure of engineering logic. They treat a predictable, localized mechanical failure as if it were weather. You know, it rains, so you use an umbrella. The belt spills, so you use a shovel.
It's basically like driving a car where the alignment is completely shot. If you hold the steering wheel perfectly straight, you aren't going to go straight. You're slowly going to drift to the right, and eventually you're going to grind against the highway guardrail.
Right.
You can't just pretend the car's supposed to go straight and then blame the guardrail for scratching your paint. The underlying tension is wrong.
That is the perfect analogy. The alignment of the car is the unequal tension caused by the dynamic load. The guardrail is the steel conveyor frame. The only difference is, instead of a 2-ton car drifting on a highway, it's a massive vulcanized belt carrying 5,000 tons of rock per hour, tearing itself apart.
But hold on. You're telling me these are billion-dollar industrial complexes running highly advanced metallurgy, employing incredibly smart engineers, and their solution to a structural engineering failure is what? To sweeping it up?
Well, no.
Surely they try to fix the drift, right?
They do attempt to fix it, yes, but their primary method is the very definition of a localized bottleneck. And it perfectly illustrates the complete disconnect between static machinery and dynamic loads.
Okay.
This actually brings us to the inadequacy of the manual mechanical take-up.
Okay, I saw this term all over the sources. Walk me through what a manual mechanical take-up actually is.
Sure. Traditionally, at the tail end of the conveyor, so the pulley where the empty belt loops back around to go under the loading zone, there are these heavy threaded mechanical bolts on either side of the pulley shaft.
Got it.
If the belt is chronically drifting to the left, a maintenance worker will physically walk out to the tail pulley, usually carrying a massive wrench.
Out into the dust while the machine is running.
Often, yes, because they need to see how the belt reacts to what they're doing. So they will tighten the threaded bolt on the left side or loosen it on the right side. What they are actually doing is physically changing the angle of the massive steel tail pulley.
Oh, I see.
The idea is to change the tension vector of the belt to actively steer it back to the center line.
So they are basically manually steering the tail pulley to counteract the drift caused by the uneven load.
Yes. But let's apply your car analogy again. Your car's alignment is shot, so it drifts right. To fix it, you don't actually fix the suspension or the alignment. You just permanently turn the steering wheel slightly to the left and lock it there.
That is a terrible way to fix a car.
It's a terrible way to fix a conveyor, too. I mean, it works for exactly as long as the conditions remain absolutely identical. If the load is exactly the same weight, placed exactly the same way, the manual adjustment might hold the belt steady. But remember, a conveyor is a dynamic load environment.
Right. The next truckload of coal that gets dumped on the belt might be wetter and heavier, or it might fall slightly heavier on the left side instead of the right.
Precisely. And suddenly, your static manual adjustment is completely wrong.
Wow.
The tension vector changes again, and now the belt violently drifts in the opposite direction, tearing into the other side of the steel frame. You just cannot use a static mechanical reliance to fix a dynamic load environment. It is an engineering fallacy.
And the operational cost of this is absurd. I mean, we have Martin Engineering case studies documenting massive plants where maintenance crews were constantly, daily, adjusting the conveyor belt at the tail pulley.
Oh yeah, it's a full-time job at some places.
They were dedicating skilled human labor to standing by a belt with a wrench, fighting a losing battle against physics. And to do this safely, if they actually follow proper safety protocols, they have to stop the conveyor to make the adjustment.
And stopping the conveyor is the cardinal sin of heavy manufacturing.
Because of the throughput.
Exactly. In a steel plant, a copper mine, or a power generation facility, throughput is everything. Unscheduled downtime can cost tens of thousands, sometimes hundreds of thousands of dollars an hour.
So they are bleeding money through spilled raw material, they're bleeding money through shredded belts, and they're bleeding money through operational downtime. Why on earth is this the accepted status quo? Why hasn't the company that built the conveyor in the first place designed a better system?
This is where the quiet architect's analysis of industrial incentives is so illuminating. To understand why the problem persists, you really have to look at the business model of the original equipment manufacturers, the OEMs.
The global giants who build and sell the massive steel conveyor structures.
Right. Heavy machinery is traditionally a low-margin capital sale. When an OEM sells a multi-million-dollar conveyor system to a mine, the initial profit margin on that raw steel structure is relatively thin. It's a highly competitive bidding process.
Okay, so they aren't making all their money on the initial sale.
Exactly. So where does the OEM actually make their long-term profit?
Let me guess. It's the razor and blades model. They sell the razor cheap and gouge you on the blades.
Exactly right. Their highly lucrative recurring revenue stream comes from scheduled maintenance contracts and, crucially, parts replacement.
I see exactly where this is going.
Right. When a belt mistracks, the friction destroys the apron seals. Those are the rubber skirts meant to contain the dust. It cracks the steel idler rollers. It destroys the mechanical bearings.
And it destroys the belt.
And eventually, yes, it shreds the vulcanized belt itself, which can cost hundreds of thousands of dollars to replace. The OEM has absolutely zero financial incentive to engineer a permanent, elegant fix for localized drift.
Because if they permanently fix the mistracking, the belt lasts 10 years instead of 2 years. They would be completely cannibalizing their own most profitable division.
It is deeply cynical, but it's perfectly rational from an economic standpoint. The plant manager is too busy fighting daily operational fires to completely redesign the fundamental engineering of the system.
And the OEM is more than happy to just sell them the expensive fire extinguisher every single time it flares up.
Exactly. It is an accepted, institutionalized bottleneck.
Okay, this perfectly sets the stage. The problem is a dynamic shift in tension. The status quo is a static manual fix that fails, and the original manufacturer is financially incentivized to just ignore it.
That's the landscape.
So we need a solution that completely bypasses the OEM entirely, requires zero human intervention, and dynamically responds to a dynamic load. And that brings us to the mechanical innovation detailed in the Martin engineering specs: automated precision adjustment tracking systems.
This is where we see true mechanical elegance. Martin Engineering recognized this massive gap between the static manual fix and the dynamic reality of the load, and they engineered a localized mechanical response that isolates the problem.
I was looking at the schematics for the Martin tracker, and the brilliance is really in its simplicity. Walk us through how this hardware actually operates, because it's completely different from the manual tail pulley adjustment.
Right. An automated precision adjustment tracking system is essentially a specialized, highly engineered roller unit. You physically remove one of the standard fixed metal idler rollers that supports the belt, and you bolt this tracking unit right into its place on the frame.
So it sits underneath the belt, supporting its weight, just like a normal roller.
Yes. But unlike a standard roller, which is rigidly fixed and points straight ahead, the entire tracker unit is mounted on a heavy-duty central pivoting axis.
Okay, so it can swivel. Kind of like a seesaw that spins left and right horizontally.
Exactly. And on the far outer edges of this pivoting tracking unit, there are two vertical sensor rollers. They sit just barely touching, or very close to, the outer edge of the thick rubber belt.
Okay, I picture it.
Now imagine a heavy load of jagged ore drops onto the belt, the center of gravity shifts, and the belt begins to drift to the left.
The thick edge of the vulcanized rubber is going to crash right into that left vertical sensor roller.
Yes. And here's the crucial mechanism. It doesn't use any electricity. It doesn't use computers or delicate sensors. It operates entirely on mechanical leverage.
Oh, that's smart.
The immense physical pressure of the drifting belt grinding against that left sensor roller pushes a lever arm. That lever arm instantly forces the entire main roller structure to pivot on its central axis.
So the force of the belt drifting left mechanically steers the roller to angle sharply to the right.
Precisely. It radically changes the tension vector at that exact localized point. By pivoting right, the heavy metal roller actively drives the rubber belt back to the center line.
It's judo. It's literally using the belt's own wandering destructive force against itself to trigger the mechanical correction.
And because it is a pure mechanical pivot, it acts as a continuous self-correcting feedback loop. The harder the belt pushes left, the harder the roller steers right.
And when it centers.
As soon as the belt centers itself, the pressure on the sensor roller vanishes, the lever arm releases, and the main roller unit pivots right back to neutral dead center. It provides immediate, continuous, microscopic adjustments without a single human ever touching a wrench.
I love that. And reading through the specs, the durability required for this thing is insane because it's absorbing the exact same violent lateral forces that were previously tearing the structural frame apart.
Oh, they have to be incredibly tough.
Martin details varying levels of ruggedness. They have standard models for lighter materials, but then they have the HD heavy-duty models designed for wider, thicker belts, moving at much higher speeds.
And then you have the XHD models, the extra heavy duty.
Right.
These are heavily armored units designed for the most extreme, brutal applications on Earth. Think about moving massive, jagged boulders of copper ore in a dusty open-pit mine, where a standard mechanical bearing would be crushed in a day.
I really want to ground this in reality because the case studies Martin provides are so illuminating. There is a specific example of India's leading integrated steel producer.
Oh, the sintering plant.
Yes, they were operating a massive sintering plant in South India. And we should clarify for you listening, sintering is essentially taking fine iron ore dust and baking it into solid clumps so it can be fed into a blast furnace.
It's an incredibly dusty, heavy, continuous process.
This specific facility was handling 14.3 million tons of bulk material per annum. Let me just repeat that, 14.3 million tons a year.
It is genuinely difficult to conceptualize that scale of material movement. It's just staggering.
It is. So the main conveyor belt feeding the sintering plant was chronically misaligned. Because the material is so dense, the drift was aggressive, and it was creating massive, dangerous piles of fugitive iron ore spillage all along the walkway.
A total mess.
They installed the automated Martin tracker. The result? It completely and permanently corrected the spillage. No more drift. No more manual labor sweeping up tons of heavy metal dust.
That's a perfect example of eliminating those manual training methods. There is another really compelling case study from an integrated steel complex producing flat and long steel.
What happened there?
Their main coal conveyor was constantly spilling fine coal dust all along the structural sides. The spillage was so rapid that they were literally forced to institute regular, highly costly operational shutdowns.
Wait, they were shutting down a whole steel complex just so a crew of humans could go in with shovels to manually clear the coal before it buried the machinery or caught on fire?
Think about the massive waste of capital that represents halting production for a broom and a shovel.
It's crazy.
So they retrofitted the line with the automated tracking system. It eliminated the mistracking entirely. That immediately eliminated the fugitive spillage, which in turn eliminated the long-term maintenance costs and completely erased the need for those manual cleanup shutdowns.
What I absolutely love about this from an engineering standpoint is the brilliance of isolation. The Quiet Architect Manifesto really harps on this concept.
Yes, it's a huge point.
To solve this multi-million-dollar problem, you don't need to rip out the concrete foundations. You don't need to overhaul the entire multi-million-dollar conveyor structure that the ODM built. It's an elegant, localized mechanical intervention. You just isolate the exact point of maximum friction and correct the tension vector right there using a bolt-on piece of hardware.
It's highly effective, but from a business perspective, this raises a massive red flag.
How so?
Well, think about it. If this bolt-on tracker is such a simple, localized, and effective fix, and if the massive multi-billion-dollar OEMs are deliberately ignoring it because they are addicted to selling replacement belts, doesn't that leave a gaping, lucrative hole in the industrial market?
Oh, absolutely. It is a massive vulnerability for the incumbents.
Exactly.
And that is exactly where the smart money is moving. This is where we shift from physical mechanics to business mechanics. I really want to dive into the playbook outlined by the Quiet Architect, because they lay out a blueprint for how a small, agile, bootstrap startup can step into these massive facilities and capture just an absurd amount of value.
The Quiet Architect's Manifesto is perhaps the most intellectually satisfying part of our source material today. It is an absolute masterclass in incentive alignment and capturing industrial control points.
The core strategy of this bootstrap solution is radical. The architect argues that a startup should completely, 100%, ignore the heavy machinery sales market. Do not try to raise venture capital to build a slightly better, slightly cheaper conveyor belt system.
Right. Don't try to compete with a global OEM giant in selling massive steel frames.
Exactly. It's classical asymmetric warfare. You never fight the entrenched incumbent where they are strong. You fight them precisely where their own financial incentives make them weak and unresponsive.
That's it exactly. The Bootstrap team focuses strictly and exclusively on localized mechanical fixes. They build a business entirely around installing these automated precision adjustment trackers.
Right. The Quiet Architect outlines 5 first principles measures for founders trying to execute this model. Let's walk through them because it flips traditional industrial sales completely upside down.
Sure. Measure number 1 is isolate the friction. This goes back to what we just discussed. Don't pitch a system replacement. Walk the line, find the exact localized point where the mechanical failure, the drift is happening, and apply the tracker fix only there.
Measure number 2 is crucial. Quantify the leak. The founder has to measure the exact weight of the fugitive spillage per hour.
This changes the entire dynamic of the conversation. You cannot walk into a stressed plant manager's office and say, hey, your conveyor makes a mess, buy my machine to clean it up. They will literally throw you out.
They don't have time for that.
No.
No.
You have to walk into their office and say, I measured conveyor number 4. It is currently spilling 2.3 tons of PRB coal per hour. That specific grade of coal trades at X dollars per ton. Therefore, you are bleeding exactly Y dollars of profit onto the dirt floor every single day.
Wow.
You shift the conversation from abstract maintenance to a highly quantifiable, immediate financial hemorrhage.
Which leads perfectly into measure number 3. And this is the absolute genius part of the playbook. Bill on recovery.
The asymmetric billing strategy. This is the mechanism you use to completely bypass the agonizing corporate purchasing bureaucracy.
I want you to really break down exactly how this billing works.
Yeah.
Because it requires abandoning the way hardware has been sold for a century.
Let's look at the traditional model. If you invent a fantastic automated tracking machine, your instinct is to go to the plant manager and try to sell them the physical hardware for, say, $15,000.
And the plant manager says, that's a great machine, but I don't have $15,000 left in my capital expenditure budget for this quarter.
Yeah.
Corporate locked my equipment budget 6 months ago. Come back next year.
Exactly. Capital expenditure requires committee approvals, ROI justifications, and endless delays. It's a grueling sales cycle.
Yeah.
But the asymmetric model sidesteps all of that entirely. The startup says to the manager, I'm not going to sell you this hardware. I'm going to lease the system to you, and I will install and maintain it myself. You pay absolutely zero upfront
They
capital.
just give them the machine.
In a sense, the catch is the invoice. The startup says, in exchange for installing this tracker for free, I will charge you a fraction, let's say 10% of the market value of the raw material that is recovered by eliminating your spillage.
Wow. Okay, so if I'm the plant manager and you install the tracker and over the course of a month, I stop $100,000 worth of premium iron ore from falling into the dirt and becoming useless fugitive material.
Right.
At the end of the month, you just send me an invoice for $10,000.
Precisely. You are never asking them to find new money to spend. You are mathematically proving that you stopped their existing money from falling on the floor, and you are simply taking a small cut of the verified savings. You are monetizing the waste that the OEM ignores.
It aligns the incentives perfectly.
Yeah.
Because think about it. If the tracker breaks and the belt starts drifting and spilling again, the startup doesn't get paid. Therefore, the startup is aggressively incentivized to ensure that belt runs perfectly straight 24/7. Meanwhile, the OEM, remember, is financially incentivized for the belt to eventually fail so they can sell a replacement.
And functionally, for the plant manager, this 10% invoice doesn't come out of their locked CapEx budget. It comes out of their operational or maintenance budget, which is much more fluid. It turns an impossible capital purchase into an easy operational yes.
The last 2 first principles measures from the architect are: prove the extension of the belt's life and remove the human risk. We are going to get really deep into the human risk in a moment because it's paramount, but proving the extension of the belt life just adds compounding ROI for the plant manager.
It's an incredible bonus.
Right. Not only did the startup save their coal, but now they don't have to spend $80,000 replacing the shredded rubber belt this fiscal year.
It's a remarkably compelling pitch. However, there is a massive logistical vulnerability in this business model.
Okay, I see the flaw here. If I am leasing you this hardware, and my entire business revenue depends on me sending you an invoice for exactly 10% of the coal I saved, how on earth do I prove that?
Exactly.
I can't just trust the plant manager's math. They're heavily incentivized to lowball the estimate to save money on my invoice. Am I supposed to have a guy standing out there with a broom and a bathroom scale, manually weighing the coal I didn't spill every day?
No, you can't do that. You have hit the fatal flaw of performance-based billing in an analog environment. If you bill on recovery, you need indisputable real-time data. And that is where the mechanical hardware has to evolve. You have to bridge this heavy, brutal 19th century mechanical world with 21st century digital intelligence.
And this introduces the marriage of heavy hardware and edge AI. The Quiet Architect details a highly specific project called the Nano-Tension Vision System.
Yes, they deployed this project targeting steel sintering plants in Maharashtra, India, which, from an engineering perspective, is the ultimate proving ground.
Because of the environment.
Oh, completely. The ambient heat, the abrasive iron dust, the vibration. If delicate technology survives in a Maharashtra steel plant, it will survive anywhere on the planet.
The setup they describe is incredibly smart because they don't use complex, fragile physical sensors. They don't have little levers or laser tripwires touching the belt because a stray rock would smash them instantly.
Right.
Instead, they mount a ruggedized, dust-proof, edge compute-enabled camera directly above the tail pulleys, looking straight down at the belt.
And let's clarify edge compute for a moment. This means the tiny computer processor inside the camera housing is doing all the complex calculations locally, right there on the dusty factory floor. It is not sending a live, high-definition video feed up to a cloud server in California to be analyzed.
Because in a heavy industrial plant, you don't have the massive internet bandwidth for streaming video, and you can't afford the latency delay anyway.
Right. And what is the camera actually doing? It's not recording video for a human security guard to watch. They trained a highly specialized, lightweight computer vision AI model for one singular task. Monitor the left and right pixel variants of the black rubber belt edge relative to the stationary gray steel frame.
It's literally just watching a line on a screen. Is the edge of the rubber staying exactly X pixels away from the frame?
Yes. It is visually, mathematically quantifying the drift in real time, 24 hours a day. And the intervention protocol they programmed is highly specific. The AI model is instructed if you detect a lateral drift of more than 5 millimeters, and that drift sustains for over 30 seconds.
The 30 seconds is key, right? It ignores a momentary bump from a heavy rock bouncing. It's looking for sustained structural tension failure.
Precisely. It filters out the noise. If that threshold is met, the camera's local computer sends a digital 5-volt signal down a wire. This signal triggers a localized pneumatic actuator.
Okay, let's break down the mechanism of a pneumatic actuator, because this is how we turn a digital thought into brute physical force.
A pneumatic actuator is essentially a heavy-duty cylinder containing a piston powered by compressed air. The factory already has high-pressure air lines running everywhere for tools.
Okay, makes sense.
When the digital signal from the AI camera hits a small electronic switch called a solenoid valve, it opens the valve. This allows 100 psi of compressed air to rush into the cylinder, slamming the internal piston forward with hundreds of pounds of force.
Wow. And that piston is physically tied to a retrofitted return idler roller under the belt. So the compressed air physically shoves the heavy steel roller to pivot, steering the belt back to the center line.
Exactly. It is an electronically triggered, AI-monitored version of the mechanical tracker. But because it has a digital brain, it generates a data trail. And this is where the asymmetric billing model becomes absolutely bulletproof.
They call it the hook model application. When the camera detects the drift and fires the pneumatic piston, the software instantly generates a notification. The plant manager, sitting in an air-conditioned office half a mile away, receives an automated SMS on their phone. Drift detected at node 4. Actuator deployed. Tension normalized.
Imagine the psychological impact of receiving that text. Historically, a text about Conveyor 4 meant, Conveyor 4 is down, spilled 10 tons of ore, send the emergency cleanup crew. Now, the text says a catastrophic problem started and I already fixed it for you. You don't need to do anything.
It builds immense, undeniable trust. But more importantly for the startup, the plant manager can log into a web dashboard that aggregates all of these localized events. It shows every time the belt drifted 5 millimeters, and it calculates the exact tonnage of material that would have spilled based on historical flow rates. The dashboard translates the saved tonnage directly into recovered revenue.
The dashboard literally generates the startup's invoice. It mathematically proves the value of the 10% cut. It is an airtight business model. However, we do have to inject a massive dose of reality here.
Yeah, because we are adding incredibly delicate electronic brains to a brutal, vibrating, dusty analog environment.
And our source from Synchronix, the Indian industrial electronics repair firm, has a mountain of data on exactly what happens when you do that. Bridging the gap between software and heavy hardware introduces an entirely new, highly complex set of vulnerabilities to the system.
I was reading through the Synchronix repair catalog, and it basically reads like a horror story for an electrical engineer. They specialize in fixing automated systems like the Bonar automated tensioning controllers, and their diagnostic logs explain exactly why these systems break down. They point out, for example, that the intense, relentless humidity in India causes PCB-level connector corrosion.
Let's explain what that means physically. A PCB is a printed circuit board, the green board inside your electronics where all the microchips live. These boards plug into each other using tiny microscopic copper pins, the connectors.
Right.
In a textile mill or a steel plant in a tropical climate, the ambient moisture mixes with chemical dust in the air. This highly corrosive mixture seeps into the camera housings or the controller boxes. Over months, it slowly rusts and corrodes those microscopic copper pins until the electrical signal simply shorts out.
So the AI brain dies not because the software failed, but because the copper rusted.
Exactly.
Synchronix also notes issues with the physical sensors. If a system uses electronic load cell sensors to measure the weight on the belt, the sheer, violent physical vibration from the heavy crusher equipment nearby causes the sensor to drift.
The vibration literally shakes the microscopic calibration of the sensor apart. The computer thinks the belt is carrying 5 tons, but it's actually carrying 2 tons, so it triggers a false correction and derails the belt itself.
And then there's the power infrastructure. Synchronix details how massive power surges from fluctuating industrial electrical grids cause PLC firmware corruption.
Yeah, a PLC is a programmable logic controller. It's the ruggedized industrial computer that takes the signal from the camera and tells the pneumatic valve to open. Its instructions are written in binary firmware. If the power grid spikes violently, that electrical surge can literally scramble the ones and zeros in the firmware memory. The computer loses its mind and triggers an emergency stop, shutting down the entire plant for no physical reason.
This sounds like a nightmare for the startup.
Yeah.
If the electronics fail, the belt spills and the invoice drops to zero.
It is a nightmare. But ironically, this vulnerability is exactly what makes the localized agile startup so lucrative and defensible.
Wait, how does hardware failure make them more valuable?
And it is the most important aspect of this entire deep dive. We mentioned earlier the physical reality of a worker walking out to the tail pulley with a giant wrench to manually adjust the mechanical take-up while the heavy machinery is running. We really need to underscore the profound, lethal danger of that status quo.
To do that, I want to share the foundational origin story from the Quiet Architect Manifesto. This is the genesis of their entire engineering philosophy, and it is gripping. The author recounts their early days as a young engineer working in a facility that manufactured actual live munitions. They were watching factory workers handle live grenades on a moving assembly line.
A literal, highly sensitive, explosive environment.
The architect wrote, "I watched factory workers handle grenades as if they were holding their breath." Fear drove that intervention. The engineer didn't look at that assembly line and think, how can I increase throughput by 4% to boost quarterly profits? They looked at the humans and felt terror.
So the architect and their engineering team designed a completely automated process utilizing a 6-axis collaborative robot. They used advanced vision systems and AI to allow the robot to handle the explosives instead of the humans.
They engineered the process to physically remove human hands from the blast radius.
Exactly. And the author notes in the manifesto that, yes, obviously, the financial savings and the increased precision mattered to the corporate executives holding the purse strings. But to the engineering team, what mattered was the message set home. The ultimate success was the ability for that factory worker to clock out and say, I reached home safe tonight.
The architect coined a term for this, restorative engineering. It's the philosophy that the highest purpose of industrial technology isn't just to replace people to cut labor costs. Its highest purpose is to restore them.
Right. It restores their physical safety, it restores their human dignity, and it permanently removes them from degrading, dangerous, or lethal operational environments.
I think about that grenade metaphor. And if we connect it back to our industrial conveyor belts, the parallel is perfect. A high-speed, high-tension industrial conveyor belt carrying thousands of tons of rock is a blast radius.
It absolutely is. The Martin engineering case studies are filled with horrifying examples of the peripheral cascading dangers of mistracking. When a belt mistracks and starts spilling raw material, it's not just neat little rocks falling. If it's spilling PRB coal dust, for example, that microscopic dust rapidly accumulates on the steel grid floors, the ladders, and the narrow walkways surrounding the machinery.
And PRB coal powder river basin coal is notorious in the energy industry. It's incredibly fine, incredibly dusty, and highly combustible.
Yes. So imagine the scenario. The belt has drifted. The spillage is piling up. Management sends a manual cleanup crew, human beings with shovels and brooms, to walk into that dark, deafening tunnel to shovel the fugitive material away while the massive belt is still running inches away from their heads.
The case studies explicitly cite massive slip and trip hazards.
Because you are walking on a steel floor coated in inches of slippery, rolling coal dust. If a worker loses their footing and slips toward the moving machinery, the consequences are unthinkable. Conveyor belts have massive, unprotected pinch points where the rubber belt meets the steel rollers. If a sleeve or a glove gets caught in that pinch point, the machinery does not stop. It will pull the human in.
And beyond the physical entanglement risk, there are immense environmental hazards. Sending humans into an enclosed tunnel filled with airborne combustible coal dust, where a single spark from a dropped steel wrench could trigger a massive dust explosion. I mean, it's madness. Sending humans into that environment daily, simply to sweep up the results of a predictable, solvable mechanical engineering failure, is an unacceptable moral and legal liability.
This is exactly why the safety pitch is the ultimate closer. Plant managers are pragmatic. They might grumble about the financial cost of lost coal, and they might mentally write off the spillage as an unavoidable cost of doing business. But they absolutely cannot and will not accept the liability of human injury or death, especially not when a proven zero-risk automated solution exists.
The narrative arc of the pitch is so powerful. The asymmetric billing, the "we only take 10% of what we save you," that gets you in the door because it bypasses the CapEx budget. It's essentially free money.
Right.
The AI dashboard generates the undeniable data that proves the financial ROI to the accounting department. But the safety pitch, looking the plant manager in the eye and saying, if you install this localized tracker, your workers never have to walk into that dark tunnel with a giant wrench while the machine is running ever again. That is what elevates the automated system from a clever financial optimization to a moral and operational necessity.
It fundamentally changes the conversation. It highlights how deeply mechanical engineering systems are intertwined with vulnerable human lives. A mechanical failure in heavy industry isn't just a loss of efficiency on a spreadsheet. It is a direct transfer of physical risk onto the human worker. Automated tracking takes that exact risk back off the shoulders of the human and puts it onto the replaceable steel machine exactly where it belongs.
It's profound, really. We started this deep dive talking about a vulcanized rubber belt slipping 4 inches to the left. We talked about friction coefficients and tension vectors, and we end up talking about human dignity. We end up talking about engineering systems specifically to make sure a worker goes home to their family with all their fingers intact, without breathing in microscopic coal dust, without holding their breath on an assembly line like they are holding a live grenade.
Engineering at its best is deeply humanistic.
Okay, let's bring this all together, because we have covered incredible ground today. We started by defining the brutal physical reality, how the chaotic, ever-changing dynamic load of bulk materials like dense iron ore and sticky coal inevitably causes uneven tension, leading to catastrophic belt drift. We saw how this drift creates violent friction, tears massive belts from 36 inches down to 32 inches, and results in mountains of expensive fugitive spillage.
And we examined exactly why the historical status quo fails. We looked at how manual mechanical take-ups at the tail pulleys are flawed because you cannot apply a static, permanent fix to a constantly fluctuating dynamic problem. And we exposed the hidden OEM bottleneck, how the massive global manufacturers are financially incentivized by their own high-margin parts replacement businesses to ignore localized permanent fixes.
We then looked at the mechanical elegance of the solution, which is automated precision trackers. We broke down how they utilize a pivoting central axis and sensor rollers to use the wandering belt's own lateral pressure to trigger mechanical leverage, actively steering it back to the center line and completely eliminating the need for manual wrench-wielding intervention.
We explored the brilliant business mechanics of the bootstrapped startup model. We saw how agile teams can bypass agonizing CapEx corporate budgets by leasing these tracking units and executing an asymmetric billing strategy, charging only a fractional percentage of the accurately recovered raw material tonnage.
We bridged the gap between heavy hardware in the future with edge AI, detailing how local vision systems monitor sub-millimeter pixel drift to trigger pneumatic compressed air actuators. This generates the undeniable digital invoice needed to prove the savings, while our synchronics data reminded us of the harsh, corrosive realities of deploying delicate electronics in high-humidity, high-vibration industrial environments.
And finally, we grounded all of this engineering and economics in the core philosophy of restorative engineering. The ultimate highest value of automation isn't just financial recovery for the shareholders. It is permanently removing human beings from the dangerous blast radius of heavy machinery.
It has been a massive journey from the dusty tail pulley of an Indian steel sintering plant to the underlying philosophy of how we value and protect human labor.
Which leaves us with a final thought for you, the listener, to mull over as we sign off. We've spent this time discussing the heavy mechanics of industrial conveyor belts, but the underlying principles of structural bottlenecks and dynamic environments apply to almost every facet of life and business.
I couldn't agree more.
So ask yourself, in your own industry, in the business you are building, or even in the daily routines of your own personal life, where are you constantly applying static manual fixes to a dynamic, ever-changing problem? What is your personal, professional version of fugitive spillage? And what would realistically happen if, instead of sending someone in with a shovel to manually sweep up the mess every single day, you took a step back and focused on fixing the underlying tension vector at the root cause?
We all want that clean, simple X-ray diagnostic. We want the easy fix. But life, much like a loaded industrial conveyor belt, is a chaotic, dynamic load. It is inevitably going to drift off-center. The only question is whether you're going to stand there every day manually fighting it with a heavy wrench, or if you are going to build a system that elegantly corrects itself. Thank you for joining us on this deep dive. Until next time, stay curious and keep looking for the hidden mechanics running the world around you.